Students, welcome to the sixth session of our third module in RAC. So students, in the previous session we have studied about refrigerants, types of refrigerants, desirable properties required for a compound to become a good refrigerant, and nomenclature of refrigerants. All these things we have studied. Now today we will move to some different types of refrigeration system apart from vapor compression system. So in this session we are going to learn a special technique called vapor absorption system. So vapor absorption system is different from vapor compression system in a sense that there is no compressor in this particular system. Instead of compressor there is an absorption system. So compressor is not used in vapor absorption system. So students, you know, compressor is a device which increases the pressure of the refrigerant with the help of work. So power has to be provided to the compressor so that it can increase the pressure of the refrigerant above the atmospheric pressure, right? Then only you can have that condensation process, and the refrigerant starts to move through the different various parts of the refrigerant cycle, and the mobility is set. This refrigerant mobility of the refrigerant is set by the compressor. Then only a pressure differential is created and the refrigerant move across all the devices to complete the cycle. But instead here we don't use compressor, so there is no requirement of power. Okay, so compressor power or compressor work is not required here. Instead of compressor we are using some other devices, and I will explain it. So this is a schematic diagram representing VARS. VARS means vapor absorption refrigeration system. So students, you can see here there is a condenser. Okay, so condenser, from condenser it comes to receiver, and receiver you already learned, and then to expansion valve and to evaporator. So after evaporator the refrigerant must go to compressor in the vapor compression system, but here it is moving to another set of equipments. So this set consists of first one an absorber, second one a pump, third one a generator, and a pressure reducing valve. So instead of compressor in vapor absorption system we are using an absorber, a pump, and generator, and what, pressure reducing valve. So these are the members of the equipments we are using instead of compressor. So what is the working of this particular system? So this system consists of the fluid used here is actually, in this system we are using ammonia as refrigerant. So ammonia will absorb heat. So heat is absorbed from the space to be refrigerated in the evaporator by ammonia. So what happens to ammonia? Ammonia forms vapor, gaseous form, right? Gaseous form. This gaseous ammonia, low pressure ammonia vapor will move to absorber, right? So in absorber you can see that in absorber there will be an absorbent called, here it is water. So water is present in absorber which absorbs NH3 gas to form an aqua ammonia solution. Aqua ammonia solution. So what happens in absorber? Absorber is here it is water. The water absorbs the NH3 gas, ammonia vapor, to form an aqua ammonia solution. So a solution is formed, and after the formation of solution the pressure of that solution gets reduced. After the mixing the pressure gets reduced, which in turn draws more ammonia vapor from evaporator. So formation of mixture means pressure is reduced. So pressure reduction means it will suck more ammonia from the evaporator, but this process is exothermic. Okay, this process is exothermic. what do you mean by exothermic process? Exothermic process means heat is released. Heat is released from absorber. Heat release. So heat release means what happens to temperature? Temperature, temperature at absorber rises, right? So students, when temperature rises means the process will be if the temperature of the absorber is raised means it will no longer be able to, the water will no longer be able to absorb ammonia. So the absorption process get hindered. So in order to maintain the temperature at a required level, we are providing a system, a cooling water system. You see a cooling water system. So this cooling water system absorbs the energy released during the formation of aqua ammonia solution. So during aqua ammonia solution formation, it is since it is an exothermic process, it releases heat. That heat release is absorbed by the cooling water in order to maintain the temperature at a required level. So more amount of mixing takes place. So this strong solution, thus it forms a strong aqueous solution. This strong solution, since it is in liquid form, a liquid pump, pump can be used to pump this to generator. So pumping means it will increase the pressure of that strong aqueous solution. So it will reach a higher pressure. So at higher pressure, it reaches the generator. So what is the process taking place in generator? Generator, we are adding some heat. So when heat is added to aqua ammonia solution, this solution get separated, means it will the aqua ammonia solution gets separated to ammonia vapor and some weak solution of aqua ammonia solution, right? So when this solution NH3H2O solution, if we add heat, it will get separated to NH3 vapor gaseous form and NH3H2O solution itself, but it will be a weak solution. This will be a strong solution, right? So after addition of heat, this weak solution will return back to the absorber through a pressure reducing valve. So why we are adding a pressure reducing valve? We are placing a pressure reducing valve in between generator and absorber because it will reduce the pressure, since because absorber is present at is at a pressure equal to that evaporator pressure, so it will be a lower pressure. So in order to make the solution to flow, we have to maintain a pressure differential. So since pump is increasing pressure, actually there should be a pressure reducing valve in order to reduce the pressure to the absorber pressure. Okay, so the weak solution comes back to the absorber and the high pressure ammonia vapor moves to condenser. So what happens in condenser? Same as that of the case with vapor compression system. The condenser will reject heat to atmosphere and it will become high pressure ammonia will become liquefied because it is getting condensed, right? It is at constant pressure, it is getting condensed, means the vapor will get will get converted into liquid form and it will pass to receiver where additional amount of liquid will be received. Okay, so this liquid will then pass through expansion valve where its pressure gets reduced to that of evaporator, and evaporator it will again absorb the heat from the space to be refrigerator and the cycle continues. So this is the process taking place in vapor absorption system. So what is the main difference, how it is different from vapor compression system? So instead of compressor, we are using a absorption system setup where which includes an absorber, a pump and a pressure reducing valve along with the generator. So the input here is nothing but heat supply. So some heat should be applied. So we don't need to apply work or mechanical work as in the case of compressor. We just need to input heat. Okay, the heat will supply the aqua ammonia solution to weak solution and vapor ammonia. So heat is a low grade work, low grade energy, low grade energy. So unlike work, heat is a low grade energy, where and at the same time work is a high grade energy. So here, with the help of low grade energy itself, we can work, we can make a refrigeration system work. So that is the main difference here. Okay. So but we are also using a pump, but comparatively comparing to compressor, the work required in pump is very low. Okay, very low. So this is the working of vapor absorption refrigeration system. So the thermodynamic requirements of a refrigerant absorbent mixture. So here the case we have studied is such a case that the refrigerant is ammonia and absorbent is water. Okay. So what are the thermodynamic requirements of a refrigerant absorbent mixture? So first requirement is that solubility requirement. It should have a high solubility in adsorbent. So what ammonia gets easily dissolved in water, so there is no such problem with aqua ammonia solution. It will be easily formed. So we can use two different fluids which won't mix together. Okay. So it should have a high solubility in absorbent, so that a strong solution highly rich in the refrigerant is formed in the absorber by absorption of the refrigerant vapor. So that is a very important requirement. Second point is that there should be a large difference in the boiling points of refrigerant and absorbent. It should be around some 200 degrees Celsius. Okay, so that only refrigerant is boiled off in the generator and absorbent alone returns into the absorber. Okay, so this ensures that only pure refrigerant circulates through a refrigerant circuit. So what is that particular point? So you can see here that there is a solution, absorbent absorbate solution or aqua ammonia solution. So we are adding heat here. So adding heat here means what is happening? The ammonia, the ammonia present in the aqua ammonia solution gets vaporized and moved to the condenser, and but the water still remains in the liquid form with some amount of ammonia, which will return back to the absorber. Why is this happening? Because there is a huge difference between the boiling point of both the fluids. So since ammonia get easily vaporized, it will form the vapor as soon as heat is applied, and it will move to the condenser, but the water still remains in the liquid form and comes back to the absorber, so that we can ensure that only pure refrigerant pass through the various components of refrigeration system. And so third point is it should have low viscosity to minimize pump work. So if the viscosity is high, means we have to increase the pump work. So we should be applying so much amount of work, then only the fluid will be set to motion. Okay. And fourth point is it should have very low freezing point. If freezing point is high, means it will get solidified easily and the pipelines will get blocked. It should have, and fifth one, it should have good chemical and thermal stability. Okay, that it should be stable. It should not disintegrate. If it disintegrates, means the system fails. And final, it should not undergo crystallization or solidification inside the system. That is obvious. If it is getting solidified, means the system gets blocked and the pipeline gets blocked. There will be choking and all. So these are the basic thermodynamic requirements for a refrigerant absorption mixture. Refrigerant absorbent mixture. Okay, refrigerant absorbent mixture. Absorbent means the fluid which absorbs the refrigerant. Okay, so the refrigerant can be termed as absorbate, and the fluid which absorbs the refrigerant is called as absorbent. Okay, so the case we have studied is having absorbent the water as absorbent. Okay, water absorbent, and refrigerant or absorbate is ammonia. Okay, that is a difference. So let us compare the two different systems, vapor compression system and vapor absorption system. So based on some criteria, first criteria is type of energy supplied. Since vapor compression system is having compressor as the device which set up a pressure differential, it should be it should be provided with the mechanical work or a high grade energy. But in absorption system we are providing heat, it means it is a low grade energy, and the energy supply here is okay, vapor compression system it will be little bit low, but in absorption system the heat supply should be high. But the main difference is wear and tear. Look at the wear and tear. Since compressor has lot of moving parts, the wear and tear will be more. That's very important. But since vapor absorption system is having generator as the main device, there is no much moving parts, so wear and tear will be less. And performance at part loads. So vapor compression system is having a little bit low performance in part loads. It will be generating the maximum output or maximum performance will be obtained only if it is working in full load. Okay, full load. But there is no such problems in case of vapor absorption system. The load won't the variation of loads won't affect the performance of vapor absorption system. And fifth one is suitability. Used your high grade mechanical energy is available. Okay, and vapor absorption system can also be used at remote places, as it can work even with a simple kerosene lamp, of course in small capacities. Okay, so the usage is this vapor absorption system can be used wherever the low grade energy like heat is available. And another important point is that charging of refrigerant is simple in case of vapor compression system, but it is difficult in case of vapor absorption system, because in uh, charging is the refilling, the filling of refrigerant. You will be learning about charging in your fourth module, and you will learn it in detail. Actually, charging is done through the suction valve of a compressor, and also so it will be easy in compression system, but it will be a bit difficult in vapor absorption system. So you will understand this point only if you study about charging in detail. So it will be coming in your fourth module, I think. Okay, and seventh one is leakage of refrigerant. So leakage of refrigerant is chances for leakage is very high in vapor combustion system, and there is no such chance in vapor absorption system, since there is no reciprocating components, such components, moving components in vapor absorption system. Since here compressor is there some chances of leak, because a large amount of pressure differential is getting created in vapor compression system, so chances of leakage will be very high. And final point, damage. Liquid traces in suction line may damage the compressor. Okay, but liquid traces of refrigerant present in piping at the exit of evaporator constitute no danger in case of. So if compressor is the if liquid, the refrigerant liquid form is induced or inducted to compressor, means the compressor will get damaged, but there is no such issues in case of vapor absorption system. So students, now now we have to calculate or obtain an expression for COP, coefficient of performance of vapor absorption system. So in order to find COP of the system, now we have to identify the various inputs and outputs of this particular system. So students, you can see there is an heat input in evaporator QE. Okay, a heat output in heat is rejected to atmosphere QC from condenser. Heat is supplied again QG to the generator, and a heat is added to pump. Heat or work, either it is actually work, but this work can be neglected because it is very small compared to these three values. So I am neglecting this. So you can write total. So there are mainly three inputs. One is QE, heat input in evaporator. This is the refrigerating effect. Second one is QG. QG is heat supplied in generator. So third one is QC, heat rejected in the condenser. So evaporator, generator and condenser, right? So now we can apply first law of thermodynamics, first law of TD, total cyclic integral of heat should be equal to 0, right? Heat transfer should be equal to 0. So you can write the only output is QC, only heat that is rejected is QC, and this QC should be equal to the sum of QG and QE, because these two are input values, this is output value. So the equation of first law of thermodynamics can be written like this: QC equal to QG plus QE, right? But we can also, since the process is all the processes are reversible, all the processes are reversible, entropy before and after the change of conditions of refrigerant remains same. Entropy before and after should remain same. Before and after should remain same. Okay. So if the temperature at evaporator is taken as TE and temperature at generator is taken as TG and condenser is TC, you can write the entropy at evaporator as entropy at compressor as QC by TC, right? QC by TC, and it should be equal to QE by Q by T is nothing but entropy. It should be equal to QE by TE plus QG by TG, right? So, but from this equation, QC can be written as QG plus QE, right? So QC is written as QG plus QE by TC equal to QE by TE plus QG by TG, right? And you can split that left hand side as QG by TC plus QE by TC is equal to, can be written as QG by TG plus QE by TE, right? So do one thing, you just group the QG terms to one side and the QE terms to other. So I am taking QG to one side, and what remains is QG into 1 by TC minus 1 by TG is equal to QE into 1 by TE minus 1 by TC, right? So this can be written as QG into TG minus TC by what? TC is equal to QE into TC minus TE by TE, right? So we can do one thing, cancel TC, right? So what remains is QG into TG minus TC by TG is equal to QE TC minus TE by TE. So QG can be written as QE into TC minus TE by TE into TG by TG minus Tc, right? Tg by Tg. Okay. So this is how we can. This is how we get an expression for heat added, heat supplied and generated in terms of heat applied or heat extracted in evaporator and various temperatures at evaporator, condenser and generator, right? So students, so our aim is to obtain coefficient of performance, right? So coefficient of performance is nothing but desired effect, right? Desired effect by input. So since we don't have work here, it shouldn't be written as work input. We just write it as input. So output by input is nothing but COP. Output is our desired effect, and input is what is input here. So what is desired effect and input in this case? So desired effect is nothing but the process taking place in evaporator, right? So this is our desired effect. The heat absorbed in evaporator, the heat should be absorbed from the space to be refrigerated by the evaporator. Thus we can generate a cooling effect in that space. So that is our desired effect. The desired effect is nothing but QE. So what is the input in this particular process? The only input is QG, heat is supplied or generated. There is a small input here also in pump, but that can be neglected. We are neglecting that work. Okay. So the output is QE and input is QG. We can write it as QE by QG. So we have the expression for QG in terms of QE. So substitute that. So COP is nothing but QE by QG, right? So QE by QG is QE into TC minus TE by TE into TG minus TC by TG. Right? So this QE and QE cancels, right? So what remains? Sorry. This is actually this should be inverse. Actually, it is raised to minus 1, right? This is Tg by Tg minus Tc, right? Tg by Tg minus Tc, not Tg minus Tc by Tg, inverse, okay? So this should be the reciprocal. So what remains is that, what remains? Te into Te by Tc minus Te and what? Tg minus Tc by Tg. So this is the term. So this is the expression for COP. COP of an vapor absorption system. COP for VAR system is obtained like this in terms of temperature. So students, while examining this particular expression, you can see that this first term resembles the expression for COP in case of a Carnot cycle, right? A reverse Carnot cycle, the refrigeration system working on a Carnot, reverse Carnot cycle resembles like this: T2 by T2 minus T1, right? So if a Carnot cycle is working in between two temperature limits, lower limit is TE and upper limit is TC, then the Carnot refrigeration cycle will have COP of this particular term, right? And what is this term? This term is nothing but efficiency of a heat engine working between two temperature TG and TC, two temperature limit TG and TC. So COP can be written in terms of, if COP can be written as COP of reverse Carnot into efficiency of Carnot, right? So COP of a vapor refrigeration vapor absorption system can be written as the product of COP of a vapor compression COP of a refrigerator working based on Carnot cycle and efficiency of a heat engine working on Carnot cycle. Okay, so this is how you obtain the expression for COP, right? So I hope you have understood the basics of vapor absorption system, its advantages, its thermodynamic requirements of the refrigerant absorbent mixture, the difference between VCR system and VAR system, the expression for COP and all. Hope you have understood. Now different types of vapor absorption systems are there. Lithium bromide. So there is a system called system working on lithium bromide as absorbent and water as the refrigerant. So water, lithium bromide plus water. Here water is refrigerant, lithium bromide is absorbent. So I think you should take this as an assignment. Try to explain the working of a vapor absorption system working based on lithium bromide and ammonia. So I'll be giving this as an assignment. And another system called electrolysis system is there, and an unconventional refrigeration system called steam jet refrigeration system is also there. So in the next session I will be explaining that electrolytic system and steam jet refrigeration system. So you don't worry about asking numerical problems based on these systems. No, it won't be asked. You should be learning the theories only. Okay, so don't worry about problems and all. So with the next session, I will be wrapping up the third module. And fourth module consists of various explanation of various components of a refrigeration system like evaporator, compressor, expansion device separately. So we will be learning those things. So hope you understood vapor absorption system, and I think I should be winding up this particular section.